Using first and second derivatives, sketch the graph of the given function by examining all the stuff that we've learned. Sometimes this can be asked as simply as investigate and graph the following function, and then you tear it apart using all these details and finally produce a highly accurate graph. So let's start with this because it actually uses the original function. The y-intercept happens when x equals 0. And if we plug 0 into this expression, we get 0 minus 0 minus 0 plus 12. That was easy. There's our first point. All this other stuff involves the derivatives, so let's knock those off. The first derivative, this is all power rules, so it goes fairly fast. 12x squared minus 6x minus 36 is the first derivative. Where is it 0? You can divide the whole thing by 6. You get 2x squared minus x minus 18 equals 0. Oops, sorry. Where did I get 18 from? 36 divided by 6 is 6. That's more like it. Okay. If I'm going to decompose this, I need two numbers that add up to -1 and multiply to -12, and those numbers are -4 and +3. Common factor for these is 2x. Common factor for these next ones is 3. And so this cleans up to x minus 2 times 2x plus 3. Now, that gives us two critical numbers for the first derivative. It's 0 when x is 2, and it's 0 when x is minus 3 over 2. The other question we're supposed to ask is, where is this derivative undefined? But this is a polynomial, they're defined everywhere. So no trouble with that. Our two critical values go on a number line. So we have minus 3 over 2. And we have positive 2. And the pieces of our derivative are x minus 2 and 2x plus 3. And technically there's a 6 involved too that I divided out up here, but 6 is positive, so it has no effect on these signs, so I'm just going to ignore that. We'll do these two factors separately, and then we'll see what the overall sign of our derivative is, f prime of x. X minus 2 goes negative, 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 0, positive. 2x plus 3 goes negative, 0, positive, positive, positive. And that means our first derivative goes plus 0, minus 0, plus. So this function is increasing, then it's flat, then it's decreasing, then it's flat, then it's increasing. Now, I didn't mention this at the beginning, but because this is a cubic with a positive leading coefficient, a shape like that is pretty much what we were expecting anyway, so to see up, down, up is not surprising. In fact, it's reassuring to see that our expectations are being borne out. All right, so for now, that's all we can get from the first derivative. I'm going to clear away some of this work, and we'll store this for a minute. We'll need it when we're doing our graph. And now we need, I just erased the first derivative, didn't I? Okay, you get to watch me do the first derivative again. Just kidding, I blipped ahead and did it. So there's our first derivative, and now the second derivative would be 24x minus 6, and where is that equal to 0? That would be when 24x equals 6, which would be when x equals 1/4. And so we get a number line that just has 1/4 on it. This should go fairly quickly. And the only piece of our second derivative is 24x minus 6. Right on 1/4, we get 0. We know that already. If x is lower than that, if it's, say, 0, we get 0 minus 6, negative. And if x is higher than 1/4, let's say it's 1 trillion, we get 24 trillion minus 6, that's positive. You can pick any number you want, but sometimes using huge numbers makes it easier to see what's going on. Okay, so this means our function is concave down, then it inflects, and then it's concave up after that, which again is the kind of behavior we expect from a cubic. We expect them to curve down for a while and then turn around and curve up for the rest of their existence. So, is that enough to do a halfway decent graph of this thing? Our y-intercept is at 12. We have at 2, at x equals 2, we have a local minimum. Oh, you know what? We need to find extrema too. When x is 2, you can see we have a local minimum here, and its coordinates will be 2 comma what? We go back here to get a y coordinate, and it's going to be 8 times 4 is 32, minus 4 times 3 is 12, minus 36 times 2, plus 12. The minus 12 and plus 12 cancel, so we just get 32 minus 72, which is minus 40. So 2 comma minus 40 is our local minimum. And we have a local max over here at minus 3 over 2. Why did it have to be a fraction? And when we plug minus 3 over 2 into our original function to get a y coordinate, we come up with I time warped that a little bit. I get 183 over 4 for the y coordinate here, which is 43, sorry, blanking here. No, 45 and 3/4. So if we're graphing this, we're going to have to go like 10, 20, 30, 40, minus 10, minus 20, minus 30, minus 40 to fit everything in. There's 50 even. So at minus 1.5, we have a local maximum at 45-ish, about there. When x is 2, we get a y coordinate at minus 40. There we go. Our y-intercept is 0, 12, which is right about there. We don't have x-intercepts, which is too bad. If we had more time and space, trying to factor this would be something to try, although cubics are not necessarily factorable, and they're often a little bit painful to factor. But this is enough already for us to see that this curve is going to come up. Local max right there, then it drops, bottoms out, and turns back, which is exactly what we expect a cubic to do. One last thing, we have this point of inflection at 1/4, so right about here is where it goes from concave down to concave up, and indeed that seems to be what the sketch is showing us. And I guess I should get a y coordinate for that as well. So right about there we have a point of inflection. Its x coordinate is 1/4. Its y coordinate will be, and once again we plug this into f of x, which is not exciting to watch, I know, but you do have to grind these out if we ask you to provide a labeled sketch. You have to find all this stuff. 1/4 is 64th times 4 is 1/16. Square this, you get 1/16, so this is minus 3/16 minus 36 times 1/4 is 9 plus 12. So we have negative 9 plus 12 is 3, Add this, you get 3 and 1/16, then subtract 3/16, and you're down to 2 and 14/16, which is 32 46/16 or 23/8. I believe that's our y coordinate. 23/8 or 2.875. We're never going to be able to show that accurately on this scale, but it looks like that height is about correct. And if they wanted the exact coordinates, now we have them. So, intervals of increase, decrease, we got them off our sine table. Local extrema, got them. Intervals of concavity, we can see them from the sine table. Inflection point, just one, we found it. And y-intercept, we got it.